Hello, and welcome to ASK Chemicals Online Academy. Today's webinar is entitled Reduce Production Costs in Large Castings with the Use of Tubular Filters. My name is Dave Heckman. I am ASK's Technical Product Manager in Feeding Systems for North America, and I'll be your moderator. Today's speaker is Ulrich Vogt. He's a technical expert in risers and filters solutions for Europe with ASK Chemicals. An agenda of the following webinar will start with some information on filtration of liquid metals, some information on filter technology, the current filtration used in large castings, some new technologies in tubular filter applications. We will then review some case studies and have a conclusion. Now, I'd like to introduce our speaker, Ulrich Vogt.
Okay, thank you very much, Dave, for introducing today's topic. Once again, a warm welcome also from my side to all listeners. Main theme is, as already mentioned from Dave, filtration of liquid metals. Today, especially at big and heavyweight castings, here also steel and iron in specific. Also, I speak only about ceramic foam filters. That means no strainers, no sieves, or something like this will be mentioned here in this webinar. As old as casting itself, the casters fight against contamination of the melt. I think that's a good sentence, and you know probably that since more than 5,000 years, perhaps also 6, 7 or something more, and yes, as long as these people pour metals, there is a fight against impurities within the melt, because to avoid any decreases at the physical properties of the castings. One part are reoxidation inclusions, which are the most commonly reported defects in steel and also in iron castings. Allow me to say a few words on this subject. Turbulences, you see it here on the picture. We all know the usually possible sources which can cause impurities, maybe from the refractory material. Sources could be the furnace, the ladle. The source could be the ingating system when you use any hollowware or something like this, and much more. But I would like to mention some sources that are sometimes less known or less noticed. Air entrainments. Left-hand picture shows simple and typical downscrew used to pour castings, and the right-hand picture shows very impressive, in my opinion, what happens during that entrapped air. You can see it here. The air entrainment during mold filling is really a main source of the oxygen that is consumed in reoxidation inclusion formation. Different investigations showed that jet velocities, that means also here the stream, the speed of the stream, what you can see on the right-hand picture here, showed that jet velocities by around 5 meters per second reach up to 1 cubic meter of air per cubic meter of the liquid. Okay, that's a water model, but you know, we have to use and we have to work with models because it makes our investigation a little bit more easier. But at the end, it is really, that means that by pouring of around 40 liters of steel, up to 20 milliliter impurities are produced only by this process. That means 20 liters of impurities, that is mostly metal oxide. That means reoxidation products. Here, the filtration comes into the game. The filtration of different molten metals and their alloys, state of the art today and the daily foundry practice. Clear, a lot of developments have been seen during the past, you know. The development of ceramic foam filters made from zirconia is one of them. But before we switch to zirconia, in ceramic foam and a little bit more go into practice, I would only mention we need also a bit theory, why filters work. You can see it here on the pictures, and we speak about the Reynolds number. This describes the ratio of the inertia of the liquid to the viscosity of the liquid. It is dimensionless, but different investigation found that the transition point from a laminar to a turbulent stream is by this number, 2300. But mostly influenced is that, sorry, by V and D. That means the speed and the diameter. There are different formulas to calculate it. And what for us, in this case, is very important is that the speed and the diameter is reduced by using foam ceramics. ASK Chemicals is manufacturing his ceramic foam filters in the high-tech plant in Alfred, New York, in US. There are made a lot of different ceramic foam filters from zirconia, from alumina, special filters, and this in different sizes. And the different sizes means from a few millimeters nearly to a half meter. The capacity we are making for is around 0.1 kilogram up to 550 tons at least. You can see on the picture here on the right hand side what we are producing, the range what we are producing in filters. Yeah, we starting with small gate filters with a size of a few millimeters, over the standard filters, typical things, 50 by 50, 75 by 75, and so forth, and up to giant tube filters, what is really, really a big piece. Let us now switch over to some basics of the technology of ceramic foam filters. Because of the typical application, that means molten metal at high temperatures and pressure at least, there are some very important requirements which the filter material must fulfill. You can see it here as on this slide. You need a chemically stable material, mostly chemical inert. It must be, of course, mechanically and thermally stable. And it must be has also a high refractoriness. Good thermal properties are also very, very important. And when we see that here, then we see that as a perfect material for these requirements, the zirconia has been identified and implemented for the manufacturing of high quality ceramic foam filters. In this case, you see the PSZ material, that is that what we are making mostly our zirconia filters from. That means partially stabilized zirconia. It is a mixture of different phases, and it is really maximized for thermal shock resistance and is mostly used as a raw material for ceramic foam filters for high pressure and load applications. As mentioned, the best ceramic material used for filtering high temperature steel and iron-based alloys is a partially stabilized zirconia, utilizing magnesium oxide as a stabilizing agent. This material exhibits excellent thermal shock resistance as described already by me, and furthermore, this material has a very good chemical, mechanical, and thermal ruggedness. Also this material is capable to withstanding the thermal shock from room temperature to 1700 degrees centigrade without creeping or melting. It is chemical inert and therefore able to withstand the corrosive effects of the alloys and the slags with which they come in contact. Of course, you will never have light without shadow when you're making any products. And one of the challenge by processing with this material is his huge shrinkage. And you see it here exactly on these pictures on the left-hand side. This green one, it is the size before firing, and the white one is after firing. We have to struggle with shrinkage rates up to 20% by this process. Some words about the ceramic foam structure and terminology. By the way, the structure contains a continuous network of voids made up of many pores in typical cells, what you can see here on the picture. The molten metal flows through these tortuous convoluted pathways, which brings the main advantages of this structure for the foundry guys by pouring, filtration, reducing of speed and pressure, and fulfill then what I mentioned before on the slide, you remember, the requirements by Reynolds number, reducing the V, the speed, and the D, and the diameter, what we have seen there on this previous slide. The ability to make the ceramic structure from high-performance oxides has allowed these materials to be optimized for the filtration of steel alloys at temperatures up to 1700 degrees centigrade. I already also mentioned that. And when you have a look on this picture, you see exactly how the structure is. You see what we called the web finger between these cells as a connection, these different pores where this structure is also built up from, and the cell, what is called the complete structure from this filter. Here once again some requirements and influencing facts which are connected with the use of ceramic foam filters. That is only a little bit more theory, but it is describing really that with which the foundry guy has to struggle every day. All these aspects are very important with the application and calculation of filters, and at the end also for the installation of the filter into the mold. I will not go too deep into this, but one important remark still here. You know that in the application of filters for large castings, it is necessary to provide correspondingly large fill areas for effective and efficient filtration. A lot of foundries use simulation software for that, but I would short mention that we also offer a simple Excel tool for a fast calculation where some digits, and you see it here on the left hand side, there are included the weight, the relevant wall thicknesses, pouring time, and so on, and that you can use very, very simple for first calculation without to use a big simulation software or something like this. It is only to give you an additional tool on the hand what you can use in this case. The filtration practice on large castings, and here I mean really between 2 and 35 tons at least, is different compared with filtration by smaller ones. Unfortunately, it is usually not possible to reduce the amount of filters to ideally match the number of filters determined by the technicians and optimal for the casting number of ingates. The ideal case would be the placement of one filter, or let me say filtration system, at each ingate, and this should always be positioned as close as possible to the ingate to use the effects of ceramic foam filter fully and completely. The manufacturing of filters meeting the requirement size in a single piece is technically challenging, bringing additional risk and failing to an economically feasible. For, let me say this and other reasons, various ways have been devised to use filters even for large castings. Some of these are short explained here. This method, what you see here on the picture, it's called, it is relatively common, let me say it this way, especially in iron foundries. It is a filter bank, and it means that standard filters are arranged side by side in a filter bank in order to accomplish the capacity you need. The picture here shows a typical installation of many filters in a row. You can see the side-by-side installation without any additional support at the joints. Yes, and no support in the filter bank, what means that there's no support on these places here between the filters, where they are joined together, is also a risk of filter breakage. And also the distribution of the metal on a filter bank is very inconsistent. We have seen that only a few filters have to filter the complete amount of liquid metal, with the rest of the filters in the row only contribute a small amount of filtration. So that means some filters are overloaded. Let us see in this case, at the next page, an interesting simulation we did with a known software for simulation processes in the foundry. We did make here simulate with tracers, and you can see here really good that the risk of filter failure caused by the different loading of the filters is not to be underestimated. When we start with the normal casting process, okay, the runner is filled more and more, and then also the first melt is running into the runners to the ingates, and then we see that the system starts really with a different distribution of the metal. This is reinforced by the lack of filter support at the joints of the filter. Also, when inserting the filters in sequence, filter bits or ceramic inclusions can break off from the surface during contact and subsequently pass into the mold. And then you can see here the next piece, the next slide. One ingot is not more really filled. That means the risk of what I mentioned before, that means air entrainment, is also here very high. And you can see here the next one not completely filled. And so it goes like a red line through the complete process once this system is completely filled. But that is really very, very important if you know it. When you use single filter side by side in a bank, you do increase really the risk for any filter breakages. And that is absolutely not to underestimate. Very, very important in my opinion. That is the reason that I want to show you this simulation pictures here. More different methods to filtrate large castings is also the use of a filter carousel, designed for use with preformed gating systems, hollowware of refractory material. Several tons of liquid metal could be filtered with a single system. In contrast of that was the relatively heavy and difficult structure of the filter carousel. Another method is the use of filters with large dimensions in so-called filter holder. They are also made from a refractory material, as you see here on the right-hand side. The use of few large filter would be an ideal case because it only takes a few perfectly tailored filters suitable to the number of ingates required. In addition, these filters could be installed relatively close to the castings and to the ingates. Unfortunately, in reality, it is not possible to manufacture ceramic filters of this size which would be needed. Above a certain size, the production is uneconomical or not possible, and all based on today's manufacturing capabilities. However, it is possible to produce ceramic foam filters up to a maximum size of, let me say, around 300 millimeter for the iron and steel casting area. But there's also a point what you have to bear in mind. It should really be noted that the thickness of the filter must be increased in parallel to the filter size. That means a filter thickness where the required priming of the filter increases so much that not enough heat can be provided by the liquid metal when it's contact the filter. This would at the end lead to an abrupt freezing of the filter and the filter is then blocked. You see here 2 pictures, what we also have experienced. The first example here, that is a zirconia filter into a filter holder. And that was short before this filter was breaking. You can see always a crack inside. And at the end, we could say it was a little bit, or we had a lot of luck here that the filter was not broken. In the second picture, what you see here, that's a filter carousel here, in this case, a corner piece, and the filter was broken. At the end, what we have to say here is really that we have a high risk of filter breakage. And that is what I mean. Each of these aforementioned applications has its dangers. And that ultimately can lead in short to an unclean or unusually scrap casting. Nobody wants it. All the filter installations listed above have one very distinct and serious similarity: the risk of the filter breakage. This is the worst case scenario of filtration applications, which often leads to a scrapping of the affected casting. It was therefore the task of avoiding this case and to design a filter which provides reliable protection from this occurrence. To reduce risk of breakages and to make it more safe, the tubular filter for using in steel and iron applications was developed. This type of ceramic foam filter combines the known advantages of the ceramic foam filters in addition to other very interesting and useful properties. You can see here on the picture, we can also produce this filter in different types and various designs, and it can be made open at both ends, like in this case here, or just open at one end. It can be also produced. In addition, the tubular filter's length and or diameter can be varied based on the need of application. Of course, they can be produced in the usual porosities and materials that reticulated foam filters are normally supplied in. Advantages, you can see it here on the left-hand side. In addition, they are really, really very, very good. That means you have a big filter area. This filter, the geometry is more or less self-supporting. It has a very compact size and construction, and some more. The risk of filter fracture is extremely minimized when you use this type of filter. This is achieved through the compact construction of the filter, what I mentioned before. The geometric shape of a tube is at least a very efficient design. The tubular filter allows molten metal to flow through from the outside to the inside, which means the entire hydrodynamic and ferrostatic pressure is on the surface of the filter, and thus acts to the idle self-supporting geometry. The destruction of the filter by fracture is greatly reduced. This way leading to a new dimension in the use of ceramic foam filters. The use and the installation of the tubular filters within the mold are very different, but no more difficult than the use of any standard plate or something like these filters. In fact, the installation of this filter is simplified because tubular filters are designed for easy installation within the mold near the mold cavity. You can also place them directly near the next ingate, or you can use a suitable filter print. Very important, if the runner and feeding system are made of hollowware, then it would be more useful to have a tailor-made housing. This would be the most ideal solution, because then you will have a more specialized and suitable system in place. And you can see it here on the pictures. That is a filter inside a housing. Only a little sketch that you can see, okay, we use these filters in this way, that we go into the housing, go around of the filter, go from outside to the inside of these filters, and then we have the outlet, or If it makes sense and if it's necessary, you can also use 2 outlets on both sides when you tilt the complete housing. You will see an application in this in a case study which we show later on this presentation. Based on this design of the tube filter and housing, the risk of filter breakage is practically eliminated. Of course, ASK is providing the data sheets to these filters and housings, which we have in different sizes and which we have with different throughputs and capacities for iron and steel. That is can be read at our internet sites, or you can also get the information from our sales force, which we will support you in any question you have, of course, with a pleasure. Yeah, another important point are the closed front faces of this filter type. We call it front edge coating. You can see that these front faces are completely closed here on both sides. And this avoids any damaging of filter structures by assembling with the houses, because the housing is made from a refractory, the filter is made from a refractory, come both together. They are very, very hard and stable, and that could lead to broken webs or a broken structure, especially when edges come together with a clash or something like this. And that means that with this edge coating, we successfully avoid any filter fingers breaking off during installation and makes the handling of the filter much more safer. I think that's a very good benefit. Combined with tubular ceramic foam filters, the system can be easily assembled without any additional adhesives or other time-consuming methods. If several housing are used per casting piece, the capacity of the system is increased and large amounts of molten metal can be safely filtered. Through the 2 exit ports, which can be closed by necessity, a right or left-sided version is no longer necessary. The complete system is very, very simple, only 3 parts, and then it is more or less nearly complete. It is easy to handle by one person. You don't need a crane or something like this, and that makes it really, really easy to use. One word also to our biggest tubular filter and housing. You see it here. This is probably the world's largest zirconia filter at the moment, as far as I know, I have to say. That is a tube filter with a length of 300 millimeter. The housing part to this, and you see it's really a very, very compact dimension and structure, and you can use it also in a simple way as already described. Yeah, and not to forget, let me come to this picture, what probably is also very interesting. It is a short look into the future of tube filters too. Currently runs some trials with 3D printed tube filters. You see here one placed in housing for iron and steel applications. And when we reach same results as by our other printed filters, we are able to double the capacities at least. What means, in this case, for a 150 tall tube filter, a capacity in steel from around 4,000 kilograms or even 4 tons for a 150 tall filter. Of course, in addition to the already mentioned advantages in using that, the system can be also integrated into appropriate simulation software. You can see it also here on this 3 pictures. For this purpose, the 3D data of the tubular housings and filters were processed for use with this software. Using this data, casting simulation can be created quickly and easily using the filter. For that, you can also use these data in different simulation software. That means the most common software they are on the market now. Yeah, we should now switch over to some case studies. I think it's probably really also from interest for the foundry guys, for the practice guys, for you. And before we start, I would say that currently tubular filters for foundry casting are used on an industrial scale, of course, and more than 1,000 tons of molten metal are currently poured through this filter time per month. Foundries use these filters on a monthly basis to produce single castings between 2 and 33 tons each. Below are some of the actual cases, which I will briefly explain. And then we start in the case studies. We will here start with iron as the liquid metal. You can see that is the casting is a rotor hub for wind power. And the first case here includes the use of the tubular filters at a large iron foundry. And to meet the high demands that are placed on the casting, foam ceramic filters were used here also. Especially in the manufacturing of large castings, what I already explained, people must install big downspool and runners. And in many cases, multiple runners are used. This can promote the generation of turbulence and consequently the risk of getting reoxidation within the molten metal. And at this point, an improved, more consistent and safer solution for filtration was needed. And to implement it, we did cast this one with 6 filters from the biggest one and also 6 housing. And the filtration was really, really successful in this case. When we switch over to another case study, also once again iron, then you see also that's also a very interesting casting. It is that are ship engines made from ductile iron. You see that, and we started at sizes of roughly 13 tons for one engine we casted, and after very positive experience and results by using tube filters, the customer developed the use of this filter step by step up to engines from to 33 tons with very positive results. You see, challenge is often similar. That means reduce machining costs. That means reduce rework. That means something like this. In much more cases, save money. And here also the result was a significant reduction of fettling costs with different amounts of and sizes of these tube filters. Now we will switch over to steel, from iron to steel. Here you can see also that the casting is called hook. Not more, not less, as a simple hook, but here really the challenge was that there is no work really allowed at the casting, and also no welding, and also grinding was allowed only in some parts of the casting. And that was the challenge we had to solve: decrease, avoid surface defects at welding, and that we could reach by implementing only one tube filter, 200 tall plus housing, and we could really make this process of manufacturing for the foundry much more safer. Another case study, also steel. It's a casting called impeller. The challenge was here really a better surface. You can see it's a very or more or less flat casting, and here we had to improve the surface of these castings, and the surface of this casting that we could reach by using also simple a tube filter of 200 tall and one housing. And here you can also see what I mentioned already before. This tube filter, this housing, is tilted by 90 degrees so that you can use both exit of that. And it was very, very easy to install, very simple for the people. And also we could save some other runners. Also very important for the producer was that the pouring time compared to the same casting without any filter had not to increase, and that we could also easily reach by using tube filter and housing. Another very interesting casting is this valve made for a power plant. And here also the challenge was to decrease the welding costs. And during the manufacturing of this casting, the foundry experienced a lot of failures at the surface. Some of these defects were identified as subsurface defects, mainly caused by non-metallic inclusions and probably too much turbulences. And of course, these defects led to an increased amount of reworking. And it was very important to bring these castings into a saleable condition. Because of it being a steel casting, a lot more effort was necessary to repair this. To reduce it, we recommended to use tube filters and housings. And after proper installation, before it has been simulated with the 3D data from the customer, they used normally simulation for their castings before. And during the process, the foundry experienced no significant increase in the pouring time, as was also previously requested. And really, the filling of the mold was very smooth. And the end was that we reached, as in case of that, approximately 55% less rework costs. Another case study, also steel, it's a casting called Pillar. And this was really also, or this is really also a big one, 20 tons, low alloy steel. And here also we had to reduce the rework, and we could reach it by implementing simple 4 tube filters and housing of the biggest type. We the effectiveness by production of these castings were increased. The rework could be reduced, and the fettling costs dropped down greatly. Okay, that was a short overview about some case studies and a little bit theory and filtration theme and something more. Let me come to a final conclusion now on this, what I the pleasure had to present you. A new optimized system for filtering large amount of metal has recently been validated at several industry-leading metal casters. This new system provides numerous advantages over the current means of filtration via standard plate shape filters, which can ultimately fail based on insufficient strength and or improper setup for the application. The use of the tubular filter represents a significant increase in security for the metal caster, investing large amounts of time and money into pouring a large iron and steel casting. And this new system provides the foundry specialist a simple but effective tool in hand. As a short outlook has been advised by new developed 3D printed tube filters with enhanced capacities. For additional and more information, of course, I recommend also to have a look at ASK Chemicals websites, where you find some technical papers, also for example reducing reducing production costs through the use of innovative filtration systems. And of course, we will also with pleasure support you in all questions concerning this tube filters in the housing system. Okay, yeah, I have to say in this case, thank you for listening. Thank you for participating. It was a pleasure for me to hold this webinar, to make this presentation, to tell you a little bit, it's really only a little bit about ceramic filters and their use. And I hope I could give you some ideas for your daily process, for your daily foundry process, and I could give a little bit help in this case. And yes, thanks you once again. And now I would give back to Dave. Thank you very much.